So for example 6, we are going to use Stokes' theorem to evaluate this circulation line integral. And before we do, I want to clarify what we mean when we say use Stokes. So we could do this line integral just straight up by parametrizing and evaluating, but that's not using Stokes. Stokes is saying, okay, instead of doing the line integral, so if it says given this, and I want to know this line integral using Stokes, then it's asking us to instead integrate over some surface, the curl dotted with the normal vector. So if it says use Stokes to find this, then you're actually going to be using this surface integral. Conversely, we could give you a problem that says find the surface integral using Stokes. So if we said find this particular flux of the curl using Stokes, then we would say, oh, okay, I'm not going to do this by actually evaluating the surface integral. I would use the line integral instead. So when we say use a theorem to find one thing, then we're asking you to write down the theorem and use the other part of the theorem to actually evaluate that thing. The other piece that I wanted you to realize is instead of writing it this way, we could have said evaluate, and I'm going to write this in one of the other forms. The other form we have is we take the I component, x squared z, and we multiply by dx plus the j component, x squared y dy plus the k component dz. This again is shorthand notation. It literally means the same thing. Both of these mean we need to actually change variables and rewrite everything in terms of t if we were going to be evaluating the actual line integral by hand. So if this problem said evaluate this using Stokes, then again it's saying, okay, don't actually evaluate this line integral, don't parameterize and switch to t. Instead, find a surface that has this curve as its boundary and do this flux of the curl integral over the surface. So one of the things that's hard about this section in particular is there's so many different ways to ask the same question, and I wanted you to just realize the different ways this may come up. Okay, so we're not doing this bottom part here. What we're basically going to do is this part here. I would like you to find a surface that has the intersection of the plane and the cylinder as its boundary, and then do a surface integral, integrating the flux of the curl over that surface. So put it on pause. This one should take you a while. This is a challenging problem. I really encourage you to let yourself think about this and let it sink in for a bit until you press play to see the solution. Okay, so let's talk through the solution to this one. The first thing we're going to notice is we want to sketch the region because it's going to be important to determine what the actual curve C is and then come up with a surface that has that C as its boundary. So in this case, the curve is caused by the intersection of the plane and the cylinder. And that means that technically the surface that has this as a boundary is the plane. This is the plane that's this yellow surface. Now, the actual boundary is coming from the shadow. When we do the line integral, or excuse me, when we do the surface integral of this plane, we are only going to integrate over this region, which is determined by the cylinder. But the actual surface we're integrating over is actually the plane. So here, we are rewriting using Stokes. We'd like to find the surface integral of the curl dotted with the normal vector. So here's my curl vector. And then this is exactly, notice what we do when we're finding the flux of some vector field. So really we're doing the flux of the curl in this, right here in this integral. And to do that, we need to identify one level surface or we want to think of the surface S as one level surface of a function of 3 variables. So that's why my G is just the plane, because the actual surface that we're going to be adding up over is just the plane. And then I'm going to project onto the XY plane. That'll be easiest. And so notice in this case, my gradient is 1, 1, 1. It is pointing outward. That's important because in order for this to hold for Stokes' theorem, I need to define my normal vector such that it follows from the right-hand rule based on how my curve is circulating. So if I put my right hand along the curve C, my thumb points outward like this, and that's the same way that this gradient is pointing. And it may be a little bit hard to see, but if we actually put axes here, X, Y, Z, I think you can see that you're pointing in the positive quadrant there. Okay, and then you want to find the rest of the components here for this integral. And so now I'm plugging through and I'm rewriting this, and it turns out then I'm going to get this double integral over this shadow in the XY plane. And so this is where the cylinder information is going to come into play when I come up with my boundaries for the surface integral. Okay, and so then we can realize it would be much easier to switch this again, do another variable change, switch it now to polar. And when we switch it to polar, we're going to end up with 81 pi over 2. So this is a lot. This is a challenging problem of thinking about how we could use Stokes' theorem to evaluate this particular line integral. It's actually the easiest way we can do it because it's pretty hard to we could parameterize this curve, but it would get into a pretty messy line integral if we parameterize this and then try to do it using a single line integral. So this is actually a much quicker way for us to do this whole problem.